I'll give you some tips for post-lab 8, the redox titration experiment. Problem number 1 is data that you will have copied down while you were performing the experiment. First of all, the molarity of the Na2C2O7 solution. This you will copy from the bottle while you're in lab. The volume of the Na2C2O4 solution, I believe, is 10 milliliters. The instructions tell you right here, 10 milliliters. That's how much you're using for each one of these experiments. So this is going to be 10 milliliters for both of these. And then you will have your initial and your final burette volumes, and then you'll be able to calculate your total burette volume. That's just going to be the difference between the initial and the final burette volumes. Then in step number 2, you need to balance the redox reaction. This is the reaction that's actually occurring while you're doing this titration. You want to make sure you balance it in acidic solution, because remember, you are adding hydrochloric acid in this titration, so you're creating an acidic solution. Get this equation balanced. You actually can't proceed forward with your calculations until it's been balanced. Then in problem number 2, you are going to copy the molarity of the Na2C2O4 solution. You'll copy it right there. You'll also copy the volume of the Na2C2O4 solution in this spot, and you'll use the molarity and the volume to calculate the moles of C2O4 2-. Remember that the molarity is always going to be the moles divided by the volume in liters. So we know the molarity and we know the volume, and that means that we can calculate the number of moles. Be a little bit careful, because your volume is in milliliters, and in the molarity equation, the volume needs to be in units of liters. So you'll need to convert your volume into liters in order to be able to use this equation. Once you have calculated the moles of C2O4 2-, you are then going to do a mole-to-mole conversion, converting into moles of MnO4-. And you're going to do that using the stoichiometric coefficients from the balanced equation that you write in problem number 2. So you're going to need to have that equation balanced so that it will give you the stoichiometric coefficients between C2O4 2- and MnO4 2-, and then you'll do a mole-to-mole conversion. In this column, you'll copy your total burette volume from problem number 1, and then in the last spot, you'll calculate the molarity of KMnO4. The molarity is going to be your moles of MnO4- divided by the volume of the solution in liters, not in milliliters. That's going to give you your molarity. And then last but not least, you'll calculate the average of these two molarities, and that's going to get transferred over to problem 7 on the next page. That's going to get transferred into this spot right here. Now also, on the next question, problem number 5, this pertains to the second titration. In this first problem, number 5, again, this is just data from the lab. So this will be the masses of the 2 iron mixtures that you worked with in the experiment, and then also your initial and final burette volumes, and you'll calculate the total burette volume for each one of these trials. Then you'll balance the redox reaction, again, in acid. And then once you get that equation balanced, you'll be able to come down to problem number 7. Remember, this is the molarity that you calculated in problem number 4, and you copied it to this data table. Your total burette volume, that's referring to that number right there, so you'll just copy those 2 trials into that spot, and then you're going to use the molarity and the volume to calculate moles. As a reminder, again, molarity is moles divided by volume in liters. We're trying to calculate moles. We know the molarity, and we know the burette volume. Again, watch out for your units, liters versus milliliters. Once you have your moles of MnO4-, you're going to do a mole-to-mole conversion into moles of Fe2+. And you're going to do that using the stoichiometric coefficients from this equation once you get it balanced. Once you know the moles of Fe2+, you are going to convert that into grams. This is going to be a gram to mole conversion using the atomic mass of iron, which is, I believe, it's 55.85 grams per mole. It is totally okay for you to use the atomic mass of the iron atom in place of the atomic mass of the iron 2+ ion. Electrons are tiny. Their mass is really insignificant compared to the mass of the protons and the neutrons. So you can use the mass of, I'm going to remove this because I'm not sure if it's right. You can use the mass of a regular iron atom and assume that that is the same as the mass of the Fe2+ ion. In this column, you're going to be recording or copying the mass of your iron mixture. And then last but not least, you'll be calculating the percent by mass of the iron 2 ion in the mixture. That is going to be calculated by taking your mass of the iron 2+ ion, dividing it by the mass of the mixture, and then you're going to need to multiply that by 100 to turn it into a percent. Now, these two numbers may not end up being the same. This is a solid mixture. Even though you shook it up and tried your best to mix it really well, it isn't uncommon for us to see students getting differences here that are even as much as 20% different. So don't be stressed out if these two numbers are pretty different from each other. That is sometimes how things work out. That said, your two solution molarities, these numbers should be pretty similar to each other, if not exactly the same.